All right, we are recording now. Let me share my screen. I'm going to this one. Okay, this one. Here. Okay, I think you're seeing my screen now. Let me just take control of the chat somewhere. All right. Okay, you can interrupt me at any time to ask questions. You can use the microphone for that. If you prefer to use the chat, I'm also taking a look at the chat. Okay, I think that's it. We can start. So this course is in infrared symmetries of general relativity. It is a quite technical course in some more formal aspects of gravity. I took a look at the student profile form some of you filled, and I know that most of you have had contact with general relativity, at least on an undergraduate level. Some of you have not, but have, and either have had no contact with relativity, in which case this is probably going to be a little bit difficult. And some of you had contact only with special relativity, which is also going to be a little bit difficult, but I think maybe manageable. And some of you are more advanced students. For advanced students, the first few lectures may be a little bit boring, especially today's lecture. And the reason is I need to construct a few prerequisites for us to actually discuss the infrared symmetries of general relativity. To be a bit more specific, the things we need to discuss first is a little bit of group theory, which some of you may already know if you are a more advanced student who has already had contact with more branches of theoretical physics. But some of you may not have had this contact, and they may not remember everything that I needed to remember, so I will cover this in more detail anyway. Then we need to discuss symmetries in the specific context of spacetimes, which needs a little bit more of differential geometry than you may be used to. So this will require me to discuss about maps between manifolds. So what is a diffeomorphism? What is a pullback? What is a push forward? Which are constructions we use to map tensors between different manifolds? What is a lead derivative, which is essential for you to discuss what is a symmetry in general relativity, and related topics. After that, we can discuss asymptotically flat spacetimes, which are the spacetimes we will be interested in to use that word infrared, or which I'm writing as ER and as IR in this blackboard, in this digital blackboard. So we need to discuss about asymptotically flat spacetimes, which are going to tell us is actually what are the spacetimes we're interested in, and how we get to the infrared region, which would be the very long distances region or very low energies, if you would rather take the point of view of field theory, for example. And once we know what is an asymptotically flat spacetime, which intuitively is a spacetime that, well, gets flat near infinity. So you need to define what is infinity, you need to define what you mean by gets flat. But the stereotypical examples of asymptotically flat spacetimes would be stars, would be black holes, would be planets, maybe galaxies, and structures like that, in which you have an isolated object in general relativity. It has a very strong field, maybe not even that strong, but it has a stronger field near the object, and it has a very faint field when you're very far away from it. So this is the general relativistic analog of when you have an isolated body, for example, in electrodynamics. In electrodynamics, you can discuss a sphere, the charged sphere, which is isolated somewhat, that's far from everything else, and this would be an isolated body in electrodynamics. It could be a sphere, it could be something more complicated, it could be a robot monkey that just places his plates. I'm not really sure what these things are called. And you can have something arbitrarily complicated but isolated. And in electrodynamics, it's easy for you to discuss this because you have already a background space-time, and you can just say that the fields get very faint when you go very far from that object, and very far is meant in the sense of the Minkowski space-time that is behind, that is in the background of those electrodynamical objects. But in general relativity, things get much more difficult because you need to discuss what is infinity when you're not really sure what space is, due to the reason that you're working in a curved space-time. So you need a more delicate construction of what you mean by infinity and what you mean for the gravitational field, which is space-time itself, to become very weak. So we will discuss asymptotically flat spacetimes. Once we know asymptotically flat spacetimes and all of this material that I need to discuss in the first few lectures, we will be able to discuss what is the Bondi-Metzner-Sachs group, which is the main group for infrared symmetries in general relativity. It is not the only option. There are a few other groups, a few other constructions which you can use to understand symmetries at infinity, but the BMS group is the main result. And after we know the BMS group, which will probably be around lecture 4, then we will be ready to discuss physical consequences and applications of BMS symmetries. These physical consequences and applications will deserve a lecture of their own, although it will probably be a little bit faster. And for this particular lecture, which will be lecture 5, I might need a few stronger prerequisites in the following sense. Some of the topics I will mention can be understood within general relativity itself, but some other topics are topics that involve quantum field theory in curved spacetimes, or they involve scattering in quantum gravity, or they involve the black hole information paradox, which may require a deeper background on quantum field theory or on quantum mechanics, and so on and so forth. I would try these applications and these consequences. I plan on discussing them on a very shallow level because each of them could be a course of their own. So I probably don't need a lot of material, but they will surely be more appreciated by those of you who already have some background in quantum field theory. So this is the structure for the course. I prepared a bunch of lecture notes about this. I will use the attendance form to send them to you later. I'll pick the emails you add to the attendance form, and I will send the lecture notes to those emails. I already sent the attendance form in the chat, but in case you lost it, I'm sending it again. And if someone enters later and asks for the form, feel free to send it to them. Although we will only accept responses to the form until the end of this lecture. After that, we will don't accept any more answers. Okay, that's the structure for the course, and I guess we can start with the introduction. So, once you have some experience with physics, you start to notice that perhaps the only reason we can do physics at all is because we enjoy a lot of symmetry. So symmetries are something that greatly simplify problems in physics and allow us to actually manage them, to actually get them to reduced to a problem that is actually solvable. In the context of general relativity, this can be seen in the stereotypical models we usually consider in a GR class, in an undergraduate GR class. So some models that we pick, for example, could be the Schwarzschild space-time, which is static and this means that it has a time translation symmetry. It is also spherically symmetric. Which means it is invariant under rotations. And these two assumptions, the assumption that it is static and the assumption that it is spherically symmetric, greatly simplify the expressions for the metric and the Einstein equations. So actually get to a model that is very simple and you can actually solve in an exact manner in general relativity. For the Schwarzschild spacetime in particular, you also impose that spacetime is in vacuum. But even if you don't assume that, you can still get a very simple solution. So for example, if you consider what we sometimes call interior solutions to the Schwarzschild geometry, this would be stellar solutions, so stars. And the basic idea is the following. You have a region here in which it is Schwarzschild. So this is the outer region. And inside, from some radial coordinates are onwards, or better saying inwards, you have here an object in which you do not have vacuum. I'm not assuming a black hole here, so I'm assuming that at some radius r, which is greater than 2 times the mass of the object, you start having this object which is no longer vacuum. So this is actually a star, and I'm assuming here a static and spherically symmetric star. In this particular case, you can also get a very simple solution, which is given by the so-called Tolman-Oppenheimer-Volkoff, or TOV, solution or metric. Oppenheimer, Volkoff. So you actually get a metric that looks, if I'm not mistaken, it has this overall form. This 1 minus 2m over r. This m is a function of r minus 1 dr2 plus the angular part. So this is the metric you actually get for a star. Both phi and m are functions of r. So this generalizes the Schwarzschild metric, and the 10 components you would originally have for the space-time metric are now reduced to only 2. So the situation is much more simple. Furthermore, both of these functions, both phi and m, are functions of r only. So the partial differential equations, which are the Einstein equations, become only ordinary differential equations. And your assumptions of symmetry simplify a lot the actual dynamics for describing the space-time. It is still a non-trivial problem to get these solutions exactly. So for example, if you're dealing with a stellar model, this will usually be very complicated functions, and perhaps you will only be able to solve for them numerically, but still you can reduce the problem of 10 coupled PDEs to just a few coupled ordinary differential equations. So the situation you get at the end ends up being much more simple, and that is thanks to the presence of symmetry in your model, to the presence of symmetry in your space-time. So this is one example of how symmetry can simplify our lives. Another common example is in cosmology, in which in cosmological models, what we usually assume is that space is isotropic and homogeneous. And these two assumptions also greatly simplify the metric, and what you eventually end up getting is what we call the Friedmann-Lemaître-Robertson-Walker metric, FLRW, sometimes called the Friedmann-Robertson-Walker metric, sometimes called the Robertson-Walker metric. This is usually due to well, in practice, it's essentially due to political reasons on the nationality of each of these guys. But in any case, what you eventually get can be written as this in this form. And here you're going to have a spatial metric, DL2, which could be that of a sphere, a hyperboloid, or the plane, the flat plane. And A is called the scale factor. So once again, you see that the 10 functions that would give the metric in Níckolas spacetime are now reduced to one single function, which is just a function of time, of cosmological time in this form. And you have the advantage that now the Einstein equations are reduced to a couple of ordinary differential equations, which can also be solved in a much more straightforward and simple way. And this is, of course, due to the presence of symmetry. And this keeps on going in essentially every area of physics in which you can enjoy some sort of symmetry, and that greatly simplifies the problem, or maybe that is exactly why you can solve the problem in the first place. So symmetry is something ubiquitous and extremely important in physics, and particularly in theoretical physics. So it is always interesting for us to understand what are the symmetries of a given situation, or which symmetry we can assume, and which symmetries we can enjoy and exploit when solving problems and when understanding a physical scenario. In the case of asymptotically flat spacetimes, you have the scenario that I had mentioned briefly before, asymptotically flat. So we have, for example, maybe you have a star or some other object in here. It could be a galaxy, it could be a planet, it could be a black hole, it could be nothing. And when you get very far, so when you get over here, the field is very faint. Even though perhaps closer here, the field can be strong in some suitable sense. And when you get to a very faint field, when the field is very weak, when you're very far away from the source of matter, which is inducing this gravitational field, you can imagine, you can wonder that probably that region of spacetime looks a lot like Minkowski spacetime. So the symmetries that I have very far away from that source should somehow resemble the Poincare symmetries of Minkowski spacetime. So in Minkowski spacetime, the symmetries we have are related to the following. So we have one symmetry, which is time translation symmetry. So this is the symmetry in which time can pass and you don't see the difference. Minkowski spacetime does not change as time passes. And for example, neither does Schwarzschild spacetime, which is a static spacetime, so the black hole just keeps existing in the same way. But this, for example, is not a symmetry in cosmological models because the universe expands. So as time passes, the universe changes. And you do have a physical difference as time passes. But in Minkowski spacetime in particular, we do have time translation symmetry. Next, we have three symmetries related to spatial translations. And what this means is that you can move through space and you can just change the origin of Minkowski spacetime, and still you will be looking at the same spacetime. This is true in cosmology because you assume that space is homogeneous, so you can move in space, you can go to a different starting point in space, you can change the origin of space without changing anything in how you observe spacetime. But this is not true, for example, in Schwarzschild spacetime, because in Schwarzschild spacetime you can be closer or farther away from the black hole, and you actually feel the difference. You actually feel different levels of attraction towards the black hole. So, for example, if you are in a rocket that is remaining stationary outside the black hole, a rocket which has its engines turned on in the sense that they keep the rocket fixed at a fixed distance from the black hole, you see that you need more power when you're close to the black hole than when you're far from the black hole. So you cannot do translations and expect the spacetime to be the same. But in Minkowski, we can. Next, we have three spatial rotations, which are just the rotations you have about, in the cases of Minkowski, about any point. And In cosmology, you also have this invariance because you assume space-time to be isotropic. And in Schwarzschild, you also have rotation invariance due to the reason that the black hole is circular symmetric. So you can actually perform rotations without changing the spacetime at all. And finally, we have 3 boost symmetries, which mean that all inertial observers in Minkowski spacetime feel the spacetime, observe the spacetime in the very same way. So you have this invariance and the boosts and the changes of reference frame. So in total, in Minkowski spacetime, we have 10 symmetries. This is actually the maximum amount of symmetries, of spacetime symmetries, that you can have in a 4-dimensional spacetime. And these 10 symmetries are known as Poincare symmetries. And in the 60s, Bondi, Metzner, and Sachs, in a few different papers actually, were trying to understand what are the symmetries of a synthetically flat spacetime. So when you get very far away from a source and the field gets very weak, what exactly are the symmetries that you still have? And as I argued up here, it is expected that in here we would have something which is Minkowski-like. So intuitively, you would expect that when the field is very weak, you're in something that resembles special relativity. So for a very weak field, we would expect that the symmetries should somehow resemble the Poincare symmetries. So they expected to have this amount of symmetries. So they expected there would be 10 symmetries associated with these ideas. And essentially, what you have here, for example, so consider the black hole again. So if you are with a black hole here, you have the Schwarzschild spacetime. If you are very far from it, the field is so weak that if you move from here to a little bit further away, you probably won't even notice. Of course, if you are precise enough, you will notice. But in the limit in which you take this distance, big R, in the limit in which big R goes to infinity, we should get a symmetry. So we should recover a translation symmetry when we get to actual infinity. In some sense, we would need to give a better definition of what is to go to infinity and what we mean by symmetry to actually make sense of this statement. But the idea is that when you go very far away from the source, you should get a symmetry again. So you should get spatial translations as a symmetry, even though the inside of the space-time, even though close to the black hole, you do not have the symmetry, in the asymptotic limit, in the infrared limit, you should get the symmetry back. And what they expected, and what everybody expected, was that you only have these 10 symmetries. It turns out that is incomplete. So the infrared symmetries, symmetry has 2 M's, are the 10 Poincare symmetries. So that guess is correct, in which the 10 Poincare symmetries are indeed symmetries, asymptotic symmetries of asymptotically flat spacetimes. But also you have infinitely many symmetries which we call super translations, which are a different sort of symmetry. They generalize the concept of translation that you have in Minkowski spacetime, and they are only exact symmetries at infinity. So their conclusion, their very unexpected conclusion, is that we go very far away from the source, or even if you consider Minkowski spacetime, and you go very far away. So when you go to infinity, in the limit in which you go to infinity, you will have not only the 10 Poincare symmetries that you have in Minkowski spacetime, you actually have infinitely many symmetries, which are composed of both the Poincare symmetries and these new super translations. And this, in principle, is very surprising and very weird and unexpected in the sense that no one would see it coming. No one would expect that you actually get infinitely many new symmetries at infinity. One of the meanings of this is that, for example, if you go very far away from a black hole, what you recover is not special relativity. And when you're very far away from all sources of gravity, what you recover is not special relativity. You get something much more complicated, which has infinitely many more symmetries. So it is a completely different theory. And the same happens in Minkowski spacetime. If you go very far away in Minkowski spacetime, in the limit in which you go infinitely far away, what you end up having is not special relativity anymore. It's this very different construction which has infinitely many symmetries. And these basic ideas at first were very surprising. And at first, when you first look into it, they just seem like an odd curiosity. So it doesn't really look like there is anything much interesting happening. It just seems like a funny curiosity that you actually get this. But it turns out in recent years, it has been shown and it has been understood that actually the presence of super translations is something very interesting and very exploitable in many different ways. So, I see the chat. What I wrote is super translations. Let me write in a slightly better handwriting. Super translations. Welcome. Okay. So we actually can exploit the super translations to understand new physics in many different ways. So for example, a few applications that I will discuss later at the final lecture are the following. You have a construction due to Dapiaggi. Let me just, Dapiaggi has two G's. I can never remember this. There's Dapiaggi, Pinamonti, and Moretti of states for QFT, quantum field theory, in co-spacetime. So what they did is they exploited the existence of super translations to construct states for quantum fields in co-spacetime. And this is interesting because when you're dealing with quantum mechanics, there are two important things in our theory. There are observables, which are, for example, energy, momentum, position, and stuff like that. And you have states, which describe what is the physical state of the system. So in classical mechanics, for example, a state would be the initial conditions, for example, for a particle. So they would be the initial position and the initial momentum of the particle. And of course, as the system evolves, the state can change depending on the point of view you have. So the particular values of position and momentum can change. And knowing those values, knowing what is the position and knowing what is the momentum, you can compute the values of all observables in your theory. So if you know the position and momentum, you can compute, for example, the energy of the particle, or you can compute the angular momentum, or, well, position and momentum itself. In classical mechanics, the distinction can be a little bit more difficult than in the quantum realm. When you get to quantum mechanics, this distinction becomes very clear. In quantum field theory in co-spacetime, it is very easy to get the observables. That is something quite straightforward to construct, but it is very difficult to construct physically reasonable states for quantum fields, especially if you are trying to do that in a mathematically rigorous manner, which is what Dapiaggi, Pinamonti, and Moretti were trying to do. So what they managed to do is to use super translations to do this. And the basic idea is that they construct a state first at infinity, and at infinity they impose that this state is invariant under super translations and under the Poincare group. And later they use this state at infinity to extend it to a state at finite distances. So that is a very intricate construction at first. using algebraic quantum field theory, but it is a very interesting construction that allows you to solve a very hard problem in quantum field theoretical spacetime, which is the construction of states, by using a very innovative method, which is imposing invariance under super translations. This is not the only application. Just to give you some year ranges here, this is probably from about 2006 to 2011-ish. So around this time, so a little something like 15 years ago, which I still consider recent. And you also have many more applications. So you have, for example, connections with what we call the gravitational memory effect, which is a prediction involving gravitational waves in general relativity. And this can be seen as a physical manifestation of super translations. So essentially what this effect means for us is that it can actually measure super translations using gravitational wave detectors. This effect has not been observed yet because it is very, very faint. And LIGO and Virgo do not have the necessary precision to measure this, and you don't have the necessary configurations. That is a bad word. You do not have the necessary configurations to measure the memory effect in individual events, but it is expected that in LIGO's observation run 5, I believe we're currently entering observation run 4. I don't really remember when observation run 5 is going to take place. But by then, we will probably be able to know whether the memory effect exists by combining data from very different events in LIGO and Virgo. And future gravitational wave detectors, such as LIGO, such as the Einstein telescope, are expected to be able to measure the memory effect in individual events. There is a question in the chat. Are there parameters associated with super translations? The way symmetries in the Poincare group are related to the amount of free parameters in the transformation matrix from one frame to another. Yes, you actually have parameters associated with super translations, but it is a little bit more difficult. So as I said, the Poincare group are related to the free parameters in the transformation matrix between frames. So you have a Lorentz matrix, which is symmetric ring matrix that needs to satisfy a few more conditions, and that gives you, in principle, 6 parameters. So the Lorentz transformations have 6 parameters, which are the parameters that go into the matrix, and you have the translations, which are 4 translations that are an inhomogeneous sum. In the case of super translations, you get something that is more complicated. They are not parameterized by parameters because there are infinitely many. So actually, you have parameterizations in terms of a function. You can associate to which super translation a function on the sphere, and I will enter in this details later. But essentially, that is the idea. I'll try to remember this later today when we get to the expressions of the Lorentz and Poincare groups. So you have this gravitational memory effect. You have other ideas, such as in quantum field theory, you have Weinberg's soft graviton theorem, which is a theorem in quantum field theory relating scattering of different particles, and it connects the scattering properties of different particles in a very specific way. By different particles, I mean specific scattering problems. So you have a few particles coming in here, they interact somehow, and some particles come out. And what Weinberg's theorem does is they relate this to the same scattering with the emission of a graviton. So this spring here denotes a graviton, or at least denotes a graviton like this for now. I may change it later if I draw anything of this sort again. And it turns out that this theorem, which is very important for you to understand the infrared structure of quantum field theories, can be understood in terms of supertranslations as well. And it goes on. You have many interesting applications of supertranslations to different topics in fundamental physics, all of them, of course, related to gravity. So supertranslations are a window to understanding different aspects of gravity, especially, of course, in the infrared, which means very small energies or very long distances. So it tells us how gravity behaves at very long distances and at very small energies. And it can be exploited in interesting applications, even in quantum field theory in space-time, which does not require quantum gravity, by means, for example, of the Piaggi-Pinamonti-Moretti construction. So I think this is enough for an introduction. So I'll start with the bits about symmetries and group theory. Something about notation and conventions that I use to avoid any confusions in the future. I use the +++ sign convention in Meissner, Thorne, and Wheeler. The first sign tells the metric I use. The other two tell about curvatures, and they won't really be that important. The metric I use is the -+++, which is the relativist metric. Okay, so this is the signs about tensor notation. I use Wald's conventions in general. Wald's general relativity. And this means that I use something that is called abstract index notation, which means I usually write tensors using Latin indices. So for example, I can write this tensor here. And these indices, they are abstract indices in a sense that they just mark the position of the tensor. You can understand them, if you will, as space-time indices, but I will use Latin indices when I do not want to choose a coordinate system, and when I'm choosing a coordinate system, when I'm writing the tensor in components rather than the abstract object that is a tensor, I'm going to write it with Greek letters. So I'll write something like this. So this here is components. This here is abstract. To give a more amicable example, an abstract notation for vectors could be, for example, V with an arrow. So this denotes the vector object. This denotes the vector as a construction in and of itself, as a geometrical object that you are considering. While if you want to write the vector in components, you would write something like this, in which now Vi is not a vector. Vi is one of the entries of the vector. So this guy here are entries, while this guy here is the full tensor. This is a very common notation in relativity, especially in the book by Wald and some in references by other authors such as Garrosh, Penrose, and the list goes on. And I find it particularly clear to distinguish when an equation holds in general and when an equation holds only in a given coordinate system. As for units, I will use what relativists call geometric units, which means in my units, we use G equals C equals 1. I won't really dive too deep into quantum mechanics here, so we don't need to bother about H bar. But this means, for example, if you're not familiar with the sorts of units, they are called, we call them geometric units, but you can also look up Planck units or natural units. And the main idea here is that we are choosing units so that this equation holds. So for example, C equals 1. This means that if I'm measuring time in seconds, then I am forcibly measuring length in light seconds. So 1 light second is the length the light travels in 1 second. So this is, so in these units, yes, you are correct. If I'm being it was asked if the vector component shouldn't have an upper index. And yes, if you want to use the relativist notation or space-time notation, indeed, it has an upper index. But in here, I was considering three-dimensional vectors in a flat space-time, so it doesn't really make that much of a difference. But yes, if we're being very precise, you are correct. So yes, be with an eye on top. So if you're measuring length in light seconds and time in seconds, then c, the speed of light, is going to be 1 light second per second by construction. I would just take a step further and completely ignore the units and just consider that c is a unitless number evaluated to 1. This is very common in theoretical physics, especially in fundamental physics, and you find it everywhere in relativity, in particle physics, and in other related areas. It is very common to do this sorts of units. In case you're not familiar, look it up. It is usually very practical because otherwise I would need to write C and G everywhere, and they don't really add any physical insight into the equations. And if you want to add them back later, you can just use dimensional analysis, and you can do that in a very straightforward manner. Okay, so these are the final comments I have. We can finally start with group theory. Any questions so far? Okay, I don't see anyone, but you can interrupt me if you have any. So we want to discuss what is the mathematical structure of symmetries, and this leads us very naturally to group theory. So the main question we want to answer now is how to describe symmetries mathematically. This is not exclusive to general relativity. I'm asking this question physics as a whole. So how do I describe physical symmetries in a mathematical manner? It could be in classical mechanics, it could be in particle physics, it could be in general relativity, it could be in any topic in physics. What should I ask of a mathematical structure to say this describes a collection of symmetries? And to answer this, it is particularly useful to choose one particular collection of symmetries and see how this collection of symmetry behaves. So what we're going to do here is we're going to pick rotations. And I'm going to pick particularly rotations in 3 dimensions. And I'm only focusing on 3 dimensions because it is intuitively simpler, but the math is completely the same if you want to go to n dimensions. So you can choose to work in whichever dimension you want. I'll just focus on 3 for concreteness. So we want to describe rotations in 3 dimensions. What characterizes a rotation in 3 dimensions? I'm going to say that the symbol R denotes a rotation, and I expect R to act for concreteness on vectors. So I'm going to apply this transformation R to a given vector V, and this is going to give me the rotated version of V. So for example, if I have this vector V over here, maybe I apply R and it brings it over here. So this is the rotated version of V. What can I ask? What do I expect of R for it to be a rotation? The first thing I will ask is that it is a homogeneous function in the sense that it doesn't see length. So if I have any constant alpha multiplying V, I expect this to be alpha times RV. And the reason is rotations do not see length. So when I rotate a vector, the only thing that is important is its direction and not exactly its magnitude. So the magnitude just factors out, and we don't expect the magnitude to have any role in the rotation. By this, I mean that we expect that the magnitudes of both the original vector and the rotated vector are the same. The next thing I'm going to ask is that if I have a sum of vectors, to have u plus v, I expect the result to also be a sum of vectors. And the reason is rotations are solid. So if I rotate two vectors, I expect that the resultant rotations also look the same, in the sense that if I originally have, for example, u and v over here, after I rotate them, I expect to still have them configured in essentially the same manner. So if I choose to add these vectors and write, for example, this vector here, I expect that the rotation also rotates that vector in precisely the same manner. So when I bring these two conditions together, I want that u plus alpha v equals ru plus alpha rv. We see that this condition is precisely that r is a linear transformation. So we're asking for linearity of the rotations. This is the first thing we're asking, but it is not the only thing. So if we rotations can be merely linear transformations, because we have linear transformations that do not look like rotations. So for example, suppose I have here again these vectors u and v, and I consider the linear transformation that takes u to the same vector, but they stretch v. This is certainly not a rotation, although it is linear, but which means that I must impose some more conditions to distinguish rotations from general linear transformations. And we're going to do this by imposing that rotations actually need to preserve something. And the thing they need to preserve, there are two things actually they need to preserve, and they are illustrated by this drawing, for example. We see that they preserve angles and they preserve lengths. So if I rotate a vector, the length of the vector before and after the rotation should be the same. And if I rotate two vectors, the angle between the vectors before and after the rotation should be the same. So that can be cast in a mathematical equation by using the scalar product. So what I'm going to ask here is that if I rotate u and I take the scalar product with the rotated version of v, this should be the very same thing as u times v. So we are preserving angles and lengths. So this is the basic condition for a rotation. We ask for a rotation to be a linear transformation and to behave in this specific way with respect to lengths and angles. We can rewrite this expression in a clever way by using the transpose of a matrix. So I'm going to consider here U as a column matrix. So a vector can be understood as a column matrix. I'm going to take this particular product here. And here I'm going to do the same. So now I'm writing this as transposes and products of matrices. I can now use the standard rules for the transpose to write this equation again in this particular form. So I have u, t, let me write a 1 in here just for convenience. 1 is the identity matrix. And you see now that if this equation is to hold for all u and v, then I necessarily need that the matrix R satisfies this particular condition. So a rotation is actually a linear transformation, which when I'm dealing with three-dimensional vectors, I can just think I'm saying linear transformations, which is the linear algebra term. But if we prefer, we can just call these matrices. So the rotations are three-dimensional matrices. Rotation in 3 dimensions are three-dimensional matrices, and they satisfy this extra condition. So I'm going to do the following. First, I'm going to denote by blackboard bold M. So that this specific notation here, it's an M with an extra leg. This guy here is the n per n times n real matrices. This is my notation for the space of n per n real matrices. And I'm going to define the collection of all rotations as being this object, which I call O of 3. 3 just denotes that I'm actually dealing with the problem in 3 dimensions. And this is going to be all matrices. They are 3 per 3, and that satisfy the condition I asked earlier. So this is the collection of all 3-dimensional rotations. Let me explain the notation a little bit. This O in here stands for orthogonal, which is the name we use for matrices, for real matrices, that satisfy this condition here. So a matrix that satisfies this condition is said to be orthogonal. So the collection of all 3 per 3 orthogonal matrix is O3, which is, we understand now, the collection of all rotations. We could be a little bit more general. If instead of walking in 3 dimensions, we chose to walk in n dimensions, then we would have gotten, by using the very same calculations, to On, which is the n-dimensional orthogonal group, which is just the group, the collection, the set of n per n real matrices, such that the matrices are orthogonal. Okay. And now that we know what is the space, what is the collection of our rotations, we would like to know what are its properties. So we can now copy its properties into a more general definition of a collection of symmetries. So what we're going to do now is to study some properties of ON or of O3. It isn't really that important. You can just choose whichever one you prefer. And we're going to use those properties to define what we call a collection of symmetries. So the first thing that is important to notice here is the following. Suppose we have 2 rotations. I'm going to call them R and S, and they're both elements of ON. Or O3, you can just plug in any cluster if you prefer. Any questions? Okay, feel free to interrupt me if you have any. So I'm going to pick 2 rotations, R and S, and they're both in ON. The first thing that is important to notice is that RS is also in ON. In symbols, the reason for this is the following. We start with RS transpose times RS. This is equal to S transpose R transpose RS. This equals S transpose identity S. This is S transpose S, and this ends up being simply the identity. So RS is an ON if R and S are in ON. I just received a question. Could it be infinite dimension? You can define something in infinite dimension, to my knowledge at least, but that would be much more subtle. And the reason is, if you actually want to deal with infinite dimension, you need to deal with infinite dimensional vector spaces, and that is the realm of something we call functional analysis. And in infinite dimensions, things are much more difficult. For example, it might happen that in infinite dimension, you won't really have R and R transpose having the same domain. So the range of R and no, I think this actually always holds. I think the range of R is always in the domain of R transpose. Yeah, maybe you can. Maybe you can. Maybe it is possible. But you do have to be a little bit more careful. You're not dealing with matrices anymore. So I don't think it makes complete sense for you to just say, oh, I'm going to pick O infinity, because there are different senses for infinity. You don't have only one infinity. So the thing that I think makes sense in this context would be, I'm going to use a little bit of jargon here, which is common in quantum mechanics, which is typically where you first encounter infinite dimensional vector spaces in physics. But what I think you could do is you pick what we call a Hilbert space, or maybe even some more general vector space, and you consider operators on this Hilbert space. So I'm now going to consider, just to not use the word, the letter R, I'm going to consider A in this Hilbert space. So A is now an operator, which is a linear transformation from the Hilbert space to itself. And I'm going to define that this guy is orthogonal if it holds, if this expression holds in a much more delicate sense, because you no longer can define the transpose in the usual sense in which you just exchange the columns and the rows. You actually have to use an inner product to define what you mean by transpose. But I think it is possible. Yes, it is possible, and it makes sense. When you're dealing with it in Hilbert spaces, in complex Hilbert spaces, instead of taking the transpose, what you actually take is the what we call the Hilbert space adjoint, and the adjoint is the transpose followed by a complex conjugation. An infinite dimension, it is a little bit more complicated. But you get to this expression, we would usually write not A, but rather a U in here. And this is what we call a unitary operator. And this plays a very important role when you're discussing symmetries in quantum mechanics, actually. So yes, it is possible. It is. I never really saw it in infinite dimensions with real vector spaces, which is the case we're dealing here now, real vector spaces. But in complex vector spaces, it is actually something very simple. I was just, it took me a while to notice what we were talking about, because at first I thought we were talking about what we call self-adjoint operators, but something was off, and then I noticed, oh no, this is actually unitary operators, which are much more simple. And in fact, you can deal with unitary operators, and you get something much more simple. Okay, I sent the present form to the wrong person. I sent it in a direct message instead of for everyone. Anyway, thanks Danielle for sending the form. So yes, you can actually define this in infinite dimensions. I never really saw it in real vector spaces, and the particular collection will probably depend on what vector space you are considering. So there isn't, at least to my knowledge, there isn't really something like O of infinity. You could talk about O of a particular vector space, more specifically of a particular Hilbert space. So you can generalize this, but in infinite dimensions, you get much more subtle. And this, in fact, plays a role. So this equation here actually is important in quantum mechanics, and it describes the basic idea for symmetries in quantum mechanics. This is what we call unitary operators. So unitary operators. But this guy is complex. So thanks. You're welcome. Okay, so getting a little bit back on track, I argued that if R and S are rotations, then mathematically at least, the composition of them is also a rotation. And a little bit more physically or phenomenologically, what I'm saying here is that if you apply a rotation S and then apply a rotation R, the result is also a rotation. This is very simple of being seen when you're dealing with plane rotations because, for example, I can start with a vector v here, and then I apply the rotation s, and it brings me here, and then I apply the rotation r, and maybe it brings me back a little bit. And you see that the overall transformation is a rotation. In 3 dimensions, it is not so easy to see this, but it is actually true. So if you rotate something and then you rotate it again, there is a rotation that takes you from the original setup to the final setup. Single rotation can take you all the way. So this is the first thing we are going to notice. So when we are dealing with symmetries, the lesson this gives us, so the lesson here, let's call it lesson 0. So lesson 0 is composition of symmetries is a symmetry. Another way of understanding this is that a symmetry is something that doesn't change the system. So if I do something that doesn't change the system, and then I do another thing that doesn't change the system, I started with S, with the system S, then I go to S prime, and then I go to S double prime. But I'm saying here that since these transformations between the system are symmetries, then I know that S and S prime are actually physically the same, and S prime is actually physically the same as S double prime. So I can conclude from these things that I can see no difference between S and S double prime. So I will assume that any collection of symmetries should have this property that composition of symmetries is a symmetry. So the first thing we learn is that a general collection of symmetries is going to be something which is a pair, G and dot, where G is a set and dot is a function from G times Cartesian G to G. So dot is something that eats 2 elements of G. So it eats, for example, it is going to take R and S, which are 2 symmetric transformations, and they're going to map it to a new symmetric transformation, RS, that also lies in G. The most important thing here is that you take 2 elements from G, and the result is still in G. So if I compose 2 rotations, I get a rotation. If I compose 2 symmetries, I get a symmetry. So this is the basic idea. So what we have so far is that a collection of symmetries needs to be a pair like this one. It is a set with an operation. If you are very, very interested in mathematical nomenclature, this sort of structure, which is just a set with an operation, is called the magma. But no one really uses this stuff. The next thing that we need to notice is that rotations actually satisfy a property called associativity. So if I apply first the rotation st, so I compose s with t, and I get this rotation st. This is a single rotation, and then I apply r. This is the same thing as I am applying first the rotation t, and then the rotation rs, and rs is also 1 single rotation. And the reason for this is that the product of matrices is associative, so you do not have to write parentheses when multiplying matrices together, and so neither do we, because rotations are matrices. Therefore, we have this property here, and we are going to ask the same thing of symmetries. The way I have for understanding this thing here is the following. So we have 3 states for the system. We have this initial state here, then we have this transform state, and the second transform state. And the connections between these guys are going to be, am I drawing the correct number of, no, I need 3. Okay, so I'm gonna add one more. So we have 4 states for the system. We are transformed between each of them. So we have first the R transformation, then the S, then the T. What this guy here is telling us is that we do this transformation here. Let me draw this right. Keep going here. While, yeah, let me add some color to it to make it easier to see. So this is the red. Okay, this is the red transformation, and we also have the blue transformation, which is this transformation here. This here is RS, this here is ST, and this is R. So the associativity axiom tells us that the red and the blue paths are the same. The way I have for understanding why this must be for symmetries is that we can also decompose these things and try to think them directly in terms of a little bit more stages. So I expect that either of these paths should be equal to the middle path, to the white path, and hence they should be equal among themselves. In math, you can't really argue like this because to say that you have the middle steps usually doesn't make sense. But in physics, at least, when we're talking about the phenomenology, when we're talking about rotations, at least to me, it seems to make sense that what you actually have is this thing here. So if I compose these 3 rotations in succession, in this particular order, so I'm applying first this function t, then this function s, then this function r, this should be the same as me composing this other things here. And the reason for this, if you want to go a little bit deeper in math, is because I'm thinking of each of these transformations as a function, and the composition of functions is always associative. So what I'm saying here now is that we can always think of symmetries as function. We can always have this idea that symmetries act. You can act with a symmetry or symmetry transformation on your physical system, and this implies that you must have associativity. This is my personal way of understanding this. If you want a less philosophical, a less phenomenological argument, which is a little bit more solid, a very strong reason for us to assume that these guys are going to be associative is that this is very, very successful. It is very convenient and very successful. If you impose associativity, you can get a lot of results out of your calculations. If you do not impose associativity, you may not have such a strong theory as you have when you do have associativity. So in practice, we essentially every time impose associativity, and I'm saying essentially because I never heard of an example, but I am assuming that maybe someone has tried to discuss symmetry without associativity, but I don't know of that. So we are going to impose this. We impose associativity. So the lesson 1 is associativity. And this means essentially that dot is associative. The next thing that we're going to notice is that 1, the identity matrix is a rotation. If I don't do anything to my system, if I don't rotate it at all, that also counts as a rotation. So that is just the action of doing nothing. And doing nothing is certainly a symmetry in the sense that I define symmetries in the sense that the system, system S, needs to be equal to the transformed system, system prime. And if I do not do nothing. If I never changed S, then surely S before and after my transformation is going to be the same. So the identity is always a symmetry. It is, in particular, it is always a rotation, and in more generality, it's always a symmetry. So lesson 2, identity. Yes, to give the mathematical nomenclatures, I said a magma, so I should also say the other names. If we have a pair G dot, so a magma, in which this holds, this is called a semigroup. And now we concluded that we need not only a semigroup, but a semigroup with an identity. And an identity means that if we pick means mathematically the following. There is some guy that we call E in the collection G, such that E times G equals G times E, which equals G for any G in G. So there is this transformation E, the symmetry E, which when I compose with any other transformation, and it doesn't matter the order of them, I always get the other transformation. So this is a transformation that does nothing. And we call this an identity. So, and the terminology for semigroup plus identity is a monoid. The next step is noticing that if R is a rotation, then reversing that rotation is also a rotation. So if I rotate something clockwise, I can always rotate it anti-clockwise by the same amount. And the same thing goes in 3 dimensions, and the same thing goes in n dimensions. If something is a rotation, then the inverse is also a rotation. And the reason for this, I never wrote the math in here, but the transpose, but 1 times the transpose, 1 transpose times 1 equals 1 times 1, which is clearly 1. And for the inverse, what you have here is that you get this expression, and the transpose of the inverse is the inverse of the transpose. So this I can write in this manner, and I can then just activate the inverse on this guy, and I'm just gonna reverse the order of the product. So I get this expression. Is this right? Yeah, this is going to lead to 1, but let me think of a simpler argument. Okay, yeah, this is a silly calculation that I just don't remember how to do it right now. But I can do it tomorrow if you will. I just won't lose time in this. But it is just playing around with the matrices. Maybe what's missing in here, you can prove that you can 2 things that you can prove is that R inverse equals R transpose, and this R symmetric. No, R is not symmetric. Okay, yeah, no, I'll just drop it, otherwise I'll lose too much time. But you can prove that the inverse is also orthogonal. Yeah, no, I have an idea. So we have R transpose equals 1 by assumption. I'm going to multiply by R minus 1 from the right. This is going to lead me to this. Then I'm going to multiply by R transpose inverse on the left. This gives me 1 equals R transpose inverse I minus 1. But the transpose and the inverse can be switched. So we get to this. Yes, and then our inverse is a rotation. There we go. Yeah, the trick is you need to start with the original matrix, not with the new matrix. Anyway, so we do have this conclusion that an inverse rotation is also a rotation, and this leads us to lesson 3. So lesson 3 is that inverses are symmetries. So what this means for us is that for any symmetry G in our collection G, big G, there is some other symmetry, which we call G minus 1, also in G, with the property that G times G minus 1 equals G minus 1 times G, which equals the identity. So this is the existence of inverses. And finally, a monoid with inverses for all elements is called a group. This is the main setup for what we want to discuss. Something that I should mention is that in nowhere I assumed that things commute. So this expression does not need to hold. So in general, you do not have a commutative property of symmetries, and in particular do not have a commutative property of rotations. So a way to picture that, let me do the demonstration. The last time I did this demonstration, I failed, and it was particularly funny. So I hope, for my sake, I hope I didn't fail. Again, for your sake, maybe I hope. But yeah, I'm using I think I can do this. Okay, so you start with the book like this, and then we're going to do 2 rotations. So first, I'm going to do this rotation, and now I vanished, okay, here. So this is one rotation, and this is the second rotation. So this is a setup with one order of rotation. So I first lifted the book forward, and then I rotated it anti-clockwise. Oh, sorry, clockwise. And this is what we get. Now, the other option is I first rotated clockwise, and then I lifted up. Okay, I got it right this time. And you see that the final configuration we get is very different, although I started in the same way and did the very same 2 rotations. And the reason is rotations do not commute. So in general, symmetries also do not have to commute. Some symmetries may commute, but that is not a necessity of all symmetries. So we cannot assume from first principles that all symmetries commute. And what you get here is then the structure of a group. Groups in which you do have commutativity are called commutative groups, or more commonly, let me write here, group plus commutative. These are usually called abelian groups. And groups are algebraic constructions, they are algebraic spaces. They're very similar to vector spaces, for example, but they're much simpler. So you see, as a first example, if you have any vector space V and you're considering the operation of addition, this is always an abelian group. And this is by definition of vector space. So all vector spaces are abelian groups with respect to addition. They're not abelian groups with respect to the scalar product, because the scalar product doesn't even take 2 copies of the vector space into itself. It takes a scalar and a vector into a vector. And what the group product does, it takes 2 group elements into a new group element, just like vector space addition. So if you take 2 vectors and you sum them, then you get, as a result, a new vector. The vector product is not a group product because it is not associative. So You do need, in this particular case, you do need to consider addition. But so yes, this is the very first example. And since they are both algebraic constructs, they have very similar ideas behind them. So for example, we can discuss what is a subgroup. A subgroup is the following. If G dot is the group, and H is a subset of G, we say that the pair H dot is a subgroup if it is a group. A very important thing to be considered here is that the group product of H is the same one of G. So I'm not allowed to change the group products between them. So what I'm doing here is this idea. I have this space which I call G, which is my group, and H is just a piece of G. And I'm considering the interactions between the elements of H are the very same that I would consider if I was looking at G, if I was looking at the bigger picture. So if under the same product H is a group, then we say that it is a subgroup. So it is a group inside a group. This is very similar to the idea of a subspace of a vector space, which is a vector space inside a vector space. The idea in here is pretty much the same. So for our first example, what we can consider here is the group that we call SOM. This is the group which is composed of matrices R of dimension n that are orthogonal, so they are rotations, but also I'm going to ask them to have determinant +1. Something important that you can show at home, if you will, is that if R is a matrix in ON, then it follows that the determinant of R equals ±1. Okay, I'm just going to show this. It is very quick. So the determinant of RTR needs to be 1. And the reason for this is because RTR needs to be the identity, and the determinant of the identity is always 1. But the determinant of a product is the product of the determinants, and the determinant of the transpose is the determinant of the original matrix. So this here can be rewritten as that R squared equals 1. Since the matrices, it doesn't really matter that the matrices are real. This is there are only 2 square roots for 1. So we conclude that R equals plus or minus 1. So you only have these 2 options, and SON is the part of ON which has positive determinant. You can show that SON is a group, and the basic idea is if R and S are in SON, we already know that these guys are in ON, so we only need to show that the determinant of the product is still 1. And the way you do that is that RS equals that R that S, which is 1 squared, which is 1. So indeed, if I take the product of 2 guys inside SON, I still have a group. I still have an element of SON, and this makes it so that SON is still a group. S in here stands for special, which is the nomenclature we usually use in group theory to mean that we are considering matrices with unit determinant. So O is for orthogonal, S is for special, N is the dimension of the group I'm considering. So these are the rotations with positive determinant, with unit determinant. The way we can think about this, let me give you an example of a matrix that is not of that form. Of a rotation that is not of the form, so I'm going to consider the rotation P in ON, which is in ON without, sorry, it's the other way around. ON minus, this is the minus for sets, minus SON. And an example for this is P. Let me take n equals 3. This is P equals to -1, 1, 1. and zeros in all the other entries. So what this matrix does is it takes here, for example, my right-handed coordinate system, and it changes it into a left-handed coordinate system. It flips only one of the axes. So this is what we call a reflection. And you see, technically, this is a rotation in the sense that it is in ON, but it is not really what we would expect of a rotation. We don't expect rotations to do this reverses, to do this reflections. So usually what people actually call the group of rotations is not ON. I lied to you, they actually call SON the group of rotations. So you may call ON orthogonal group if you want to be if you want to give it a special name. That would be the usual name for it. So the group of rotations is SON. And just to give a little bit more insight inside ON and SON, you can picture ON as being formed by two continuous pieces. So it has this blob over here, which has that r equals -1. And you have this blob over here, which has that r equals +1. This guy here is SON. So you have these two pieces. When you apply a reflection, you can jump from one of them to the other, and the identity is somewhere in here. Since the identity is in here, this means that this guy has no identity. Well, that is actually quite a sad thing to say. So, but anyway, this guy doesn't have an identity. So since it doesn't have an identity, it cannot be a group. So this guy here is not a group. This guy here is a group. It is SON. So you have these two pieces of ON. And how can I make it rigorous, this idea of pieces, of continuous pieces of a group? And to discuss that, I need to go into what we call a Lie group. A Lie group is something a bit more complicated. And now I'm going to use a word that is very common in relativity, but I don't know if all of you are familiar with it. I may use this word a few times. But Lie group G dot is a group that is also a manifold. I know that 90% of the people at the school are Brazilians, so let me say that manifold in Portuguese is variedade. Just in case you know this word in Portuguese but not in English, or the other way around. So a group that is also a manifold such that the following operations are smooth, such that dot this is the operation that takes G and G2, G2, G1 dot G2, and I'm going to ask for a different operation, which is the inverse, which takes an element to its inverse, or smooth. Okay, so I'm asking here that this is a Lie group is a smooth group. By that I mean that I not only have an algebraic structure, not only I have this group structure, I also have a structure that tells me that the group is continuous, and even more than continuous, it is differentiable, and it is, of course, smooth. So I want to be able to differentiate as many times as I want functions on the group. So the word manifold refers to that. Manifold is the construction in differential geometry which allows me to take derivatives and other constructions of calculus in a general space. A manifold, I like to think of a manifold as the most general space in which we can do calculus, in which we can calculate derivatives, we can calculate integrals and stuff like that. So in general relativity, space-time is a four-dimensional manifold. And by that I mean that space-time can be curved, so it doesn't need to be flat, it doesn't need to be Euclidean. but I still am able to do calculus on that because I want to write, for example, derivatives. The Einstein equations involve derivatives. They are partial differential equations. I want to write integrals and stuff like that. So I want to be able to do calculus. So a manifold is a space in which you can do calculus. That is the most general space in which you can do calculus. And what I want for calling something a Lie group is that it is a group, but it's also a manifold. So it is a group in which I can do calculus. And furthermore, I have here a notion of continuity, and that is implied actually by the manifold structure. So if I have a manifold, I have a notion of continuity. In this case, we're implicitly taking the manifold to have a differential structure, right? So not only topological, but also differentiable. Yes. When I say, yeah, I didn't write it here. It is more detailed in my notes, but I should have written in here too. I usually think of only smooth manifolds, but yes, we are focusing on a smooth manifold. For those of you who are not familiar with this term, the reason one of the participants raised this question is because there is also a notion of a topological manifold, which you can also call a continuous manifold, which is a manifold in which you can't really do calculus yet. It sort of looks like a manifold in which you can do calculus, but it didn't give it the necessary structure to do calculus yet. It may not be possible to give it a structure to do calculus. So my way of explaining what is a manifold can break when you're discussing a continuous manifold or topological manifold. But yes, to discuss a Lie group, we want a smooth manifold. If I'm not mistaken, a group that is also a topological manifold and in which this product, these operations are continuous, is called a topological group. I believe that is so, but I'm not fully sure. But I'm actually quite certain. But I never really studied topological groups, so I may be missing a detail or two. In any case, we are interested in Lie groups, and Lie groups are smooth manifolds. So we can do calculus, we can differentiate, we can integrate in these groups. And this means, and they're interested in Lie groups. There are two things here that interest us in Lie groups. The first thing is that these are usually the groups that appear in fundamental physics. So there are other branches of physics. There are other scenarios in which you can deal with groups that are not Lie groups. So you can deal with what we call discrete groups. But for our applications, for our cases, we will deal only with Lie groups. So there's no reason for us to bother about other sorts of groups. And the other reason, from a more mathematical standpoint, is that when you consider a Lie group rather than a general group, this actually gives a very powerful theory. So you can deal with the theory of manifolds, which would be differential geometry. You can deal with group theory, which would be the study of groups. But when you bring both of them together, when you have both a group structure and the structure of a smooth manifold, you have a lot of structure. So this actually gives astonishing results. It gives very powerful results. And from a mathematical standpoint, it is a quite interesting object due to this aspect. But for our purposes, our main interest in these groups is going to be the fact that they are the ones that actually appear for us. So to give an example, as I said, ON and SON are Lie groups. So what happens is that ON is not connected. This is the topological term for saying that it has many pieces, while SON is connected. Since you are used to relativity, you probably know that you can always add coordinates to a manifold, so you can always describe a manifold in coordinates. And to that end, you can do this with rotations as well. This is given in terms. One example are the so-called Euler angles. These are three angles that you can use to parameterize any rotation. They are not exactly This leads to very interesting consequences due to the fact that the Euler angles do not live in the same topological space that is SON. So more specifically, let us consider the case of SO3. SO3 is what we call the real projective space, RP3. So it is the three-dimensional real projective space. And the Euler angles live in the 3 torus. And this leads, this difference in the particular topological aspects of these 2 spaces leads to a very interesting consequence called gimbal lock. But I won't dive into those details in here. I'm just really excited about this topic. But so okay, you have these constructions, and now let me get. I think I won't have enough time to discuss everything I wanted, but I can now start getting to the topics that really interest us the most, which are the Lorentz and Poincare groups. So first we have the Lorentz group, and what we're going to consider here is we want to consider transformations of coordinates. So I'm going to have this coordinates x mu, and I'm going to take them to x prime mu, and I'm going to consider that the transformation is linear. This is just for to make the problem a little bit simpler. So we're going to consider these things here. We're going to consider that the transformation is linear. So we can write it in this notation. Okay, so I'm using Einstein's summation notation, which means that if I'm not writing, if I'm writing twice the same symbol, one up like here and one down like here, this means that hidden in here there is a summation symbol going from 0 through 3. Okay, so we have this expression here. It is a general transformation of the most general linear transformation of coordinates. And I want to ask something further in here, which is the following. If I transform the coordinates of the Minkowski metric, I'm gonna end up with n prime rho sigma, which is going to be given for a general coordinate transformation by this expression here. X prime nu, x sigma, and is this correct? I think no. No, the primes are in the other way around. So here we're gonna have this thing here, or yeah, I can just consider the inverse transformation. So let me just take this guys out here. I'm gonna put this guys here, put this guy here, and this guy here. So this is the original coordinates, and these are the new coordinates here. They are related by these expressions here. Since I'm considering a linear transformation, this gets simplified to lambda mu rho, lambda mu sigma, eta mu sigma. I'm going to ask to further simplify this transformation. I'm going to ask that the transformed version equals the original version. So I'm going to ask, and there are other transformations that do not satisfy this, but I'm going to ask that this thing holds. So I'm asking something a little bit stronger. When I do this, I can use the following notation. I will write the components of eta as this matrix eta, which are just given in Cartesian coordinates by this thing here. So this is the Minkowski metric matrix. And now I can write these guys in the following form. I can write them. I never recall what is the correct order. Here it is. It's just transpose times eta times lambda. So lambda here is the matrix whose entries are given by lambda eta sigma. Okay, so the way I can see this here is I'm going to rewrite this guy a little bit, just move things around, but I'm not really going to change the expression in any significant way. So you see, I am contracting here this guy with this guy, and this guy with the guy on the other way.
since this here is in the reversed order and it's a transpose, well, this guy here is just the matrix itself. So this becomes this, eta becomes eta, and this guy becomes transpose. And we get this expression here. So what we get now is this space, this group actually, which I'm going to call O31, which is composed of four-dimensional matrices such that lambda transpose eta lambda equals eta. Notice this is very similar to what we had with rotation. So with rotations, we had R transposed identity, R equals identity. So now I have this slightly different thing. And this is what we call the 3-1 pseudo orthogonal group. For this particular case, we also for the particular case 3-1, we also call it the Lorentz group. Could the elements of eta be order constants instead of minus plus plus plus? Or okay, so to give the first answer, I know you're talking about something more general, but just to start with the simpler case, you could consider, for example, plus minus minus minus. This is the first modification you could do, and you see that this is just adding a minus sign to both sides here, so you get the very same group, but we will call it instead O13. The reason is that the 3 refers to the number of positive signs and the 1 refers to the number of negative signs. So we do have these two notations, but they're actually the same group. But there are other constructions that you can do with them that are not really equivalent. And that includes, for example, when you're dealing with spinors in quantum field theory, you have two different ways of discussing them. And they are not equivalent in a straightforward manner. Of course, if you're taking track of all of the signs, you will get the same results. But in the intermediate calculations, they are going to look a little bit different. So for example, if you know what is the Dirac equation, you can see that the Dirac equation in Weinberg's book, in Weinberg's quantum field theory book, looks a little bit different than the Dirac equation in Pascal and Schroeder's quantum field theory book. And the reason is each of them uses a different metric signature convention. Weinberg uses the same convention I'm using, while Pascal and Schroeder uses the particle physicist convention, which is plus, minus, minus, minus. And this leads to differences in the appearance of the Dirac equation. So there is this first modification. And then there is the more general modification, which is what I think you're thinking about, which would be to change this guy in the metric to, for example, A, B, C, D, where these guys, I'm assuming, are real. If they're complex, you can do a few different things, but this is the most important thing. And the key point here, what actually makes a whole lot of difference in here, is that eta is not really a matrix. So the way I actually want to define these groups is not with matrices. And here I'm writing them with matrices, but this is the simplified form. The way these groups are actually defined uses the object eta, which is a tensor. And by this, I mean that eta is actually a function that eats two vectors, so u and v, and spits out a number, spits out a real number. And the way you actually define those groups would be the lambdas such that this thing holds. So this is quite similar to what I wrote earlier with the scalar product for rotations. And when you do this, it turns out that you can always choose a basis in which all of these coefficients are either plus or minus 1. So the case with plus or minus 1s is the most general case. It's the most general possible case. And the reason for this is that this is not really a matrix. This is actually a tensor. and this means they can be manipulated in different ways. So when you diagonalize a matrix, you cannot change the eigenvalues. But when you diagonalize a 0-2 tensor, you can always make the eigenvalues, in quotation marks, be plus or minus 1. So you actually end up with these equivalences. So the most general case of these groups that we can deal with would be the groups, the pseudo-orthogonal groups O, P, Q. I'm assuming here that we're dealing with real matrices. So we're dealing with real spaces, and you end up with this general case. So P and Q are only the numbers of positive and negative signs along the diagonal. You're welcome. We're in the case where we have zeros, but that's in physical since we don't deal with vectors that are orthogonal to themselves, right? In fact, in this very same course, we are going to deal with spaces in which you have zeros in the diagonal. So this is the general semi-Riemannian case, but there are situations in which you may be interested in metrics which look like 0, and then, for example, we are going to deal with the case in which we have 0 plus 1 plus 1. This is the metric of a new hypersurface. So if you consider, for example, Minkowski spacetime, and you consider the surface x minus c equals 0, this surface has a metric that looks like this. This is what we call a degenerate metric or a Carolean metric. And that is a case of particular interest for us specifically. But the usual discussion of pseudo-orthogonal groups does not cover this case. So I'm not going to mention it right now. I think you can discuss things like this, and you're probably, if I recall correctly, when you add this 0 in here, so you're in this more complicated scenario in which you have zeros in the tensor you're dealing with, then the group ends up being infinite dimensional. What do I mean by infinite dimensional? We're talking about Lie groups. So Lie groups are manifolds, and a manifold has a well-defined dimension in the sense that is given by the number of coordinates that I need to specify a point. You actually have a more precise definition, but I'm not going to go into it here right now. But for example, if I have a manifold like this, I need 2 coordinates to specify this point here, for example. So this is a 2-dimensional manifold. If I have something like this, this is a 1-dimensional manifold because I only need 1 number. If I have more general constructions, such as 3-dimensional space, I need 3 coordinates, so it is a 3-dimensional manifold, and so on and so forth. So what happens is that usually in the traditional case, the semi-Riemannian case, where you only have plus and minus ones, this guy here is going to be finite dimensional. If you add a 0, if I recall correctly, it becomes infinite dimensional. And this is one of the origins for us having super translations. The reason is that infinity, when we go to infinity, we actually get into a new hypersurface. So we get into a surface that looks a lot like this thing here. And due to this issue, you end up with infinity, with an infinitely dimensional group. Okay, so this is the Lorentz group. Anything else? But yes, something important to mention here also, which is if you pick the Lorentz group, you're going to notice that inside the Lorentz group, you have some quite interesting matrices. For example, you have this matrix here, which is 1, 0, 0, 0, 0, 0, 0, R, where R is an orthogonal matrix. Why is this interesting? Because you have, for example, for this particular lambda, that this holds. Is this correct? Yeah, I'm quite sure this is correct. So you're going to have a property like this. Or better saying, ignore this property. I'm not really sure about it right now. I don't want to prove it. So let's just focus on this. And here you see that this family of lambdas, they are matrices. They are going to compose in the very same sort. So if you have here, let's call this lambda R. If you have lambda R, lambda S, the product of them is going to be 1 RS. So you see that the family of this lambda R's here is essentially the same thing as the orthogonal group. So this is essentially O3. However, if you want to be very technical and precise, you may argue that this is not really O3 because O3 is made of 3 by 3 matrices, while this here is a 4 by 4 matrix. So this isn't really an element of O3. But we should be able to understand it as an element of O3 in some way. The way we do this is by using a concept known as a homomorphism, which is the group theory version of a linear transformation. So if we have G and H groups, I'm now assuming that the products are understood instead of writing them explicitly every time. I'm going to say that a function phi from G to H is a homomorphism. Homomorphism. If it holds that phi of G1, G2 equals to phi of G1 times phi of G2. So what this thing means is that I can compute the product inside G or later inside H, and the result is the same. So in here I compute the product first in G, and then I map it to H. And here I first map it to H, and then I compute the product in H, and the result is the same. So this is what I call homomorphism. This is very similar to a linear transformation, which would have, for example, U plus V equals LU plus LV. So if I just change the notation here to this, you see that I get essentially the same thing. Yes? Okay. So a homomorphism is the group theoretical version of a linear transformation. In fact, homomorphism is a general name for these sorts of things. And you could actually call a linear transformation a vector space homomorphism. So this is what we call homomorphism. Then we have also what we call an isomorphism. Isomorphism. This is an invertible homomorphism. If a homomorphism is invertible, it holds that the inverse is also a homomorphism. And this is a particular property of algebraic structure. So, for example, the inverse of a linear transformation is a linear transformation, but this doesn't really hold in general for other mathematical constructions. So, for example, in differential geometry, you have what we call diffeomorphisms, which we're going to talk about later in the second class, if I get to the end of this soon enough. And the inverse of a diffeomorphism doesn't need to be a diffeomorphism. But the inverse of a homomorphism is always a homomorphism. So in terms of isomorphism, we can now discuss the idea I had, which is the following. If we take this collection of matrices here, which is R, where R lives in O3, this is isomorphic to O3, which means that it is, as far as algebra goes, they are essentially the same thing. And they are when I say that they are isomorphic, what I mean is that there exists an isomorphism phi that takes this guy here to this guy here. So this guy, I'm saying that it is a homomorphism. More than that, it is invertible. So it is an isomorphism. And when we say that two groups are isomorphic, this essentially means that as far as algebra goes, the two groups are pretty much the same thing. So they're essentially the same group. Yeah, I'll just finish the discussion about the Lorentz group, and then we can continue with the Poincaré group tomorrow. And what I want to say about the Lorentz group is the following. We defined earlier the group SON for ON, and now we can discuss also the groups SOPQ for OPQ. I'm going to focus in the particular case of the Lorentz group, which is the one that actually interests us the most. So what I have here now is going to be that SO31 equals lambda is an O31, and the determinant of lambda equals +1. You can also show that this here implies that that's lambda equals plus or minus 1. But this is not all the story. Because you see, if we pick the group O31, we don't have only two connected components. We don't have only two pieces. We have four. We have this piece, this piece, this piece, and this piece. They're all copies of each other, up to a few reflections and stuff like that. So what we have here is first, let us call this, I will call this SO plus 31. I'll explain the plus soon enough. So this is the original piece. This is the piece that has the identity. Now I have two possible transformations I can make. The first is a spatial reflection. The other one is a time reflection. And then I can compose both of them. Okay, so this here has spatial reflections, this here has time reflections, this here has both. So in this guy's here, in this guy, in this guy, time runs backwards. And in this guy, we're using a left-handed coordinate system rather than a right-handed one. So you have these four pieces, but you see that only one of them is really, how can I say it? Is really original, so to speak. The other ones are copies. This one here is the original piece. The other ones are just copies of two reflections. If we impose that the determinant is plus or minus 1, what we are actually saying is that we are either in the original piece or in this piece. So either I didn't reflect anything at all, or I reflected twice. Because now that I'm dealing with four-dimensional matrices, I can consider, for example, this transformation here. This is a Lorentz transformation, but it reflects space due to this entry here, and it reflects time due to this entry here. Still, it has positive determinant. So we're actually also going to define what we call the orthogonal Lorentz group. SO is called the proper Lorentz group. So this is the proper. This is the orthogonal. And this guy here is defined as lambda in O31, such that lambda 0, 0, the first entry, is positive. It doesn't need to be 1, it can be any number. The only restriction I'm making is it is positive. And you can show that it can never be 0. So we actually are imposing this restriction here. So who are each of these guys in here? So we have SO plus, which is this guy. Let me just make some confusion. So this guy here in blue, this guy is SO31. This guy here is O plus 31. And you see now that I'm going to make the very natural definition that SO plus 31 equals SO 31 intersected with O plus 31. So this is what we call the proper orthogonal Lorentz group. This is the Lorentz group you're actually interested in. This is what we're going to consider. And the reason is that if you want to include the order transformations, if you want to include reflections, if you want to include time reversals, you can do this later. We are interested mostly in the continuous structure of the group, not really in the discrete properties of reflections and time reversals. So we can focus on this particular guy, and we consider whatever else happens later. There is another reason to consider this guy, which is that in nature, the space-time is actually invariant. The whole group, so O31 is a symmetry of Minkowski space-time, but it is not a symmetry of particle physics. And the reason is that weak interactions actually violate parity, which is spatial reflections, and time reversal symmetries. So to be a little bit more precise, when the weak interactions only care about left-handed particles. What does this mean? If you have a particle here, this could be an electron or a neutrino, or a quark. Quarks also interact weakly. So what is important here is that you're dealing with the weak interactions. And this particle here, it has some momentum, p. Okay, so this is the momentum. This particle, since we're dealing with weak interactions, the particles we're considering are fermions. More specifically, they have spin half. I won't really mind what is the physical meaning of spin in here, but essentially you can think of it as the intrinsic angular momentum of the particle. So when I say that a particle has spin half, a way for you to understand it is that it's always spinning. So it is always rotating a little bit. And this little bit is measured by the value of the spin. So an electron, a neutrino, a quark, they're always spinning a little bit. And hence, I have two possibilities. I have here my electron, and it has this momentum. And then I have two possibilities. Either it is rotating in this way, or it is rotating in the other way. If it is rotating in this way, this means that the angular momentum of this particle points to the same direction as the momentum. Otherwise, it is pointing backwards. And this here is what we call a right-handed particle. And this here is what we call a left-handed particle. So we have these two possibilities. It is either right-handed or left-handed. And it turns out, for reasons that only nature knows why, that the weak interactions only occur for left-handed particles. So if you have an electron that is rotating in this way, it is a right-handed electron, it will not interact weakly. If it is rotating in this way, it might. Furthermore, we are not aware of the existence of right-handed neutrinos. The standard model does not include any right-handed neutrinos. So as far as we know, right-handed neutrinos may not exist. They also may exist, and we have not seen them. But important point in here is this, that weak interactions actually care about whether something is left-handed or right-handed. And if you make a reflection, if you make a spatial reflection, you're going to change that. You're going to change who is right-handed and who is left-handed. Because the direction of spinning is going to change. So if I have this guy here spinning in this direction, if I grab a mirror and put it here, it is actually going to be rotating in the other direction. So I flip left and right-handed when I add a mirror, when I reflect stuff. So reflections actually change fundamental interactions, even though they do not change the space-time itself. So for this sorts of reasons, it is also more interesting in fundamental physics to consider the proper orthogonal Lorentz group than the full Lorentz group, because fundamental interactions actually violate some transformations, some symmetries from the full Lorentz group. Okay, I'm already past time. I still wanted to say some things for today, but I surely want to do this so fastly. So I think it's a better idea to keep it for tomorrow and see how things go. Unless there are any more questions, I'm going to end the meeting. Yeah, I'll first stop recording and ask for questions again. But while we're still recording, are there any questions? Okay, it doesn't seem to be the case, at least not with the recording on. So I'll first stop the recording and then we can ask it again. Let me just see here. Stop recording.